But I want you to think about this. So let's think. Let me draw a fun picture over here. And you're going to see very quickly that it didn't really matter a whole lot that I knew or didn't know exactly what was at a given spot until I examined it. So check this out. Let's think carefully about why it is the case that linear search, in fact, will correctly output true if X is in L. So just a reminder, remember to notice found is set to false at the beginning. So if X is not found yet, found is not updated, right? It still stays false. That seems pretty straightforward, right? At least I hope that is. So just notice this. This is an important detail. So now, take a look at this. So suppose you have this array. And suppose that we had our lucky 7 was sitting right here. Suppose that that's where X is. Okay, in the first iteration of that, if we walk through carefully what we did earlier, in the first iteration of this loop, it starts off at I at 0. So what it will do is it examines this position and says, uh-oh, in that position, there is nothing, right? So then it proceeds to the next spot and checks if L sub I is equal to X. Well, notice the next spot doesn't have X in it. So, oops. Go to the next one. Okay, there's nothing there. I'm going to keep going. Notice each iteration, there's something interesting going on here. Does anybody see it? Do you notice that every time I don't find one, notice that, or even heck, if I do, notice that every time I do one iteration of this loop, I've examined all the ones to the left of the position I'm looking at. So for example, when I check this position, all of these ones are already examined. Does everybody see that? So it's the same idea we talked about a little earlier, just that, but we've got to be a little more rigorous about this. We can't just simply just assert that, oh yeah, the algorithm for sure will check all of them. We need some way of connecting this up to that the algorithm actually does. So that's kind of our high-level description. We need an actual explanation. Like that's a high-level explanation. We want a formal one. So naturally you would check this one, that doesn't match. But notice that it gets to the last one, and then you say, hey, look, it's right there. But notice that I have had to have checked all of these to have encountered that true value of X, right? Where all of these other ones, I didn't find it. So here's something we can think about. So let's think about how many iterations are going to be happening here. So notice that it starts off at 0 and it goes up to n minus 1. But notice that if I consider each one of these, do you notice that when I go through each one of those, I'm going to examine L sub I is equal to X. So notice, so this is the invariant here, is after. So suppose I look at one iteration of this, say some value of t that's going to occur for this loop. After t iterations of the loop, found is going to be set to be true. So found is equal to true. So it's actually set to be true. Now I must stress that this I literally mean it's equal to it. It's set to be true if and only if. That means whatever is going to be right here follows if and only if. As in, if this is the case, then whatever's going to, I say after if and only if will also be the case. If this is not the case, then whatever's going to come after the if and only if was also not true. If and only if if x is in L sub 0 all the way up to t minus 1. So if I look at my iteration, so after this iteration, so for example, after the iteration, after say one iteration, what this is saying is that you've checked L sub 0. That's it. Just that's the only part of it you've examined. But after 2 iterations, you'll notice that I will have examined L sub 0 and I've also examined L sub 1. Does everybody see that? So if you're wondering, this is going to be going over the following range. So keep in mind, remember that if we have it where we have no iterations that have happened, it still has to be the case that it's false, right? So keep in mind that this value of t, it ranges from 0 all the way up to n. So when you plug in t is equal to n, then you get 0 to n minus 1, right? And that's exactly the kind of thing you're looking for, right? Because when this finishes, you've had to have examined all the positions. Keep in mind, you can easily modify this algorithm so that you just exit when you have everything. So the meaning that you got the true result. So this is the big piece that makes this work. Now, you might say, Dan, that's pretty nice, but how exactly do you prove that that is actually the case? So let's talk about this. We're going to prove this using the principle of mathematical induction. So it's going to eerily remind you of the actual algorithm's execution. To prove the correctness of the algorithm, if I can prove this property, then we're done. Does everybody see that? Because this algorithm over there runs in finite time. Linear search runs in finite time. You can prove this by arguing, quite simply, hey, look, notice that every line of our algorithm finishes in a constant amount of time, except for that loop. So notice that how many times does the loop perform iterations? Well, it performs exactly n iterations for that loop, which is a finite number. So the whole algorithm has to terminate in finite time. So this is the key part for the correctness, meaning it's going to output correctly. Because you just simply plug in when t is n, right? And that matches up when at the end of that execution of the algorithm, right? So if we have that, then we're all done. That's all we need. To prove the correctness of the algorithm, this, remember, to be clear, what it means for the algorithm to be correct is that for every instance of our search problem, so every one of them, the array, value, length, I gave it to this algorithm. This algorithm has to produce correct output. So it has to present me an answer for every single one of those instances and has to be correct, meaning the output matches the solution. So we must show that linear search sets found equal to true if and only if, I'm going to abbreviate if and only if with IFF like this, if and only if element X is in the following range. It's in this subarray, L sub 0 to -1, which I must stress that this is an empty array. Well, what's the thing? This array that I've written here, because notice that the starting index and the end index, this is the end index, is less than the starting index. So there's no elements here. So surely X can't be in any of this, right? And this is also the case that notice that that 0 iterations have happened as well. So keep that in mind. So just to keep this brief, so observe that X is not present as L sub 0 to negative 1 contains no elements. Right? So what does this imply? This implies all I have to do it now at this stage, because we know there's no elements at all, right? That we can look at. So all we have to do is show that found is not true. That's all I have to do. So all we have to do is show that found is not equal to true. But what did we say earlier? Well, let me put a star beside that. Notice that found is set to false at the beginning. So if x is not found yet, found is not updated. But notice that no iterations have happened yet. So this has to be true, right? So I'm going to say by star, found is false, proving S of 0. Piece of cake, right? That it almost feels like I'm cheating, right? It's like there's no iteration, so I obviously cannot have it, so it's true. But notice that this is because of the way I described the algorithm to you. Does everybody see that? So that brings me to talking about the actual induction. So that's the part that's really fascinating about this. And it will feel like what I did here. So every time I examined an element, I extended how much I knew about whether x is in the array or not. But keep in mind, like I said, x may appear several times in the array. The point is it's a part of the subarray. So every time I do an iteration, this expands out by 1. So if we think about this carefully, every time I consider the next element, it's almost like I have all of these ones here already, and I'm just extending the range I have by 1 after one iteration. So perhaps I can use that information to help me prove what we call the induction step or inductive step. So let's do that. So another way you can look at this is, instead of thinking about it in terms of the entire array, just think of any one step in the array when we consider linear search. And this is what I was suggesting is more a rigorous way of thinking about this. Is that each time I do one of these iterations, well, you already have, like say for example, I'm going to consider this one in the current iteration. Well, it means I already looked at all of these, right? So whenever I consider the next one, okay, there's this plus all of this that I've now considered after that iteration, right? So let's kind of put this into words. So given S of k, I'm going to show you that S of k plus 1 follows. So if S of k, then S of k plus 1. So we're going to fix some k greater than or equal to 0, because I want to have the first rung in there. So the biggest rung I initially climbed up to, and up in this case. So I'm going to fix some k greater or equal to 0. And then we're going to assume that S of k holds. Now I must stress, when I write out S of k, what I'm saying is everywhere in this statement you're going to put k. So we're going to assume that S of k holds. This is what we're going to call our inductive hypothesis or induction hypothesis. So I'm going to abbreviate this as IH. Comma, so that we can prove, sorry, my we is just melting here today, so that we can prove S of k plus 1, which I'm going to write this out because I think it's rather important for you to see it. So after k plus 1 iterations, iterations of the loop found, I was about to write false, found is assigned to be true if and only if what? What is it? That x is in this range. L sub 0 all the way up to k. So it would be positions, so box 0, box 1, box 2, all the way up to box k. Notice the indexing. So please take note of that. And I'm not just trying to prove this. I'm trying to show that this follows. That's an important part of this. So I'm going to show you that if S of k, then S of k plus 1. So I'm going to use S of k to help me prove S of k plus 1, because if I know what S of 0 is true, and I could show you from arbitrary rung to go from S of 0 to S of 1, then the same thing should be able to tell me, the same part of this proof should be able to show me how to go to S of 1 to S of 2, S of 2 to S of 3, S of 3, S of 4, and so on to any arbitrary step to a sufficiently needed size. So in our case, we just want it when we have S of n. If we have S of n, we're done. So I want you to observe that there's really only two possibilities that can happen. So the first possibility is that x is in fact in this range. But it's not just in L, it's not in this range entirely. It's not like all of this. It's actually only a part of this. It's all of this up to the previous position to this one, akin to what I drew in that rectangle over there. And this one right here. Suppose that I have all of this, and suppose I tell you it's right in there. Suppose it's in there. Then, well, what does that mean? Well, this range it's saying that if S of k, so remember S of k tells me after k iterations of the loop, found is true if and only if x is in this range, but k is k minus 1, right? Notice it's the same one right here. But what does that mean? If this is the case where it is in it, then it most certainly, the algorithms, the induction hypothesis is enough to get that. Then by the induction hypothesis or inductive hypothesis, after k iterations, found is assigned to be true. So found is equal to true at that stage. But one other thing I need you to notice, if we go back to the algorithm over there, did you ever see me reset found? Found never gets reset. So as soon as it becomes true, it always stays true. So I'll say variable found is never reset to false. False. So after k plus 1 iterations, found is still going to be true, as desired, right? Because so what I'm trying to do is I'm trying to show you that if I know what happens with the first k iterations, so after the k iterations, I want to show you that the algorithm still is correct after k plus 1 iterations. So if this happens where x is already in, say, this box right here, so this is like your k iterations, after k iterations you get this. If you want that one extra one, what I'm saying is if it's already in here, notice that it never resets found to true. Sorry, found to false, my apologies. Then that means that it's always going to be that it stays true, even when I go to this one, even if it doesn't actually match it. So if x is in here, it's going to set it to true right about here, and then it will never change it from true. So that's how we know that we're okay. Analogously, this would also say to us that if we don't find x yet, then it's still false, right? But right now we're trying to see if it's in there. So now there's only one other possibility that can happen now. Suppose that now, so we know it's in this range, but what if it isn't in this range? There's only two possibilities here. It's either in this range or it isn't in this range. If it isn't in this range, there's a possibility that x could be right here or it could not be. That's really the natural thing to think about here. So x is not in L sub 0 k minus 1. So we just have the same thing. We can just use the inductive hypothesis or induction hypothesis. And this will feel like you're just executing out those iterations because of the nature of the claim. At least I like to think of it like that. After k iterations, found is still false, right? So found is equal to false right now. And there's only two possibilities that now remain for this case. It could be that x is in the next spot, or it's not. And if we can figure out what happens in those two cases, then we're good. We're good for this induction step. And instead of n, let's say, so let me reiterate. X is not in this range by the induction hypothesis after k iterations. Found equals false. Actually, let's put the and back in. And after k plus 1 iterations, either L sub k is equal to x or L sub k is not equal to x. That's the only two possibilities after the k plus first iteration. These are the only two things that can happen. So all you have to do at this stage, I'm not going to write it here, but consider the case when L sub k is equal to x. If it is, what it will do is the algorithm will set found to be true in that step, which will give you as desired that we have for our invariant, right? It says that, so if this is equal to x, then it's saying, so the algorithm will set found to be true in that case. And as we've established, in all those other spots, it wasn't there, but it's in this spot because we've considered this possibility. If it isn't, then we know that found is still false because of what we just said right here. So it's still false. So it still remains false, which also is what we need and is required by this claim, right? This says that found is set to true if and only if x is in that range, but it isn't in that range, so x is still false, because that's the only other possibility. So this would, with these two things together, so I'll let you think about that one part there. So I'm going to put some dots here. So I'll say thus completing the inductive step. And now once you have this, you can now use the principal mathematical induction to prove the correctness of the algorithm. So all we have to do at this stage is you plug in, so you use the principal mathematical induction to prove this invariant holds for all the values we've talked about. And in particular, you just say, okay, well, if it's true for all of them, then consider, because we have an array of length n, then consider S of n. And in S of n, that is when you consider all of the elements, right? And then the linear search algorithm is correct. And that's how you'd finish off this proof. That's pretty sweet. So you can look at this proof as some parts of it I would encourage you to fill in. So it's more of a thing where we had fun doing it together. But let's talk about the time complexity for linear search now. And I must stress that there's several ways to describe linear search. This is one variant of it. You could easily have it where instead it returns a position, or you can also even have this one change where it actually exits out this loop using a so-called break statement. You could even have it return at that spot and say return true. The way I designed this algorithm for you was to deliberately make it so it's easier for me to prove this invariant. Once you have this invariant, it shouldn't be very hard for somebody to be convinced that any one of those changes won't change the correctness. So, that being said, let's talk about the time complexity of this. So notice that if we look at this algorithm, we already established this terminates in finite time, correct? So all I need to do now is measure how many operations are happening. So there's this return statement, there's this found statement here. These two together, they take some constant number of operations. We'll call them C1. There's C1 many operations here. Notice that this takes constant time, that takes constant time. Likewise, if I look at what's inside the for loop, evaluating and checking if this is equal to x, this takes constant time. And even if I had to evaluate this, would take constant time. So all of this takes some C2 many operations. So I must stress that we have to look at this in terms of the worst case, right? We want to know how much time is required to solve this problem, right? For our given algorithm, we want to know how much. So I've just measured out how long these would take with respect to the input size, which is what we classically do if we were trying to measure it in this way. So let's talk about this now. In the worst case, what would happen? What would happen? Let's think back to this issue around the boxes here. So let's think about the boxes. So when I did this, I swept all the way through from left to right. That's what this algorithm does, right? Well, what happens in the worst case is that x simply doesn't exist, right? That means you have to examine every one of the boxes, all of them. So in the worst case, scenario, which you need to identify these instances, the ones that cause the algorithm to take as long as possible, performs the most number of operations. If you can do that, then you know how long this algorithm requires to execute. So if x is not in L, that's the worst case, because this will now the way I wrote out this algorithm doesn't make any difference. But if you take any version of this where you simply have it where it returns here, or say in other versions, there's several other ways you could rewrite this algorithm. The point is that it does the same thing. It ultimately will still have it where it examines each one of the spots. If it finds it, it will tell you, yeah, there it is. But the point I'm getting at is that these are all different ways of describing the same process. It's just I did something deliberate here to make this easier for us to understand. But if x is not an L, notice that this will never set this to true, meaning that regardless, even if I try to put shortcuts into this algorithm, meaning I make it so it returns found right here if it gets a match, even if that happens, if x is not L, it would force it to do every iteration of this loop. But for our version here, it wouldn't matter. It always will do all the same number of operations. Hopefully that is clear. Regardless, I like to identify a scenario where this causes the most number of operations. But here we go. How many iterations happen here? Complete iterations. Well, n of them, right? So I have n times C2. So if I put this all together into a complexity function, the complexity here, now keep in mind there's several ways you can count this. This is just one such way. You'll end up with the same complexity function if, for example, I counted them by operation count, or I counted the extra iteration of this loop. It does, like if I was doing the conditional check for the for loop, for example. I would get C1 plus C2 times n. And if you look at this very quickly, this is a linear function. This is a linear function. This runs in big O of n time. In fact, it runs also in big theta of n time as well. In fact, you can also show that on average, if you were to add that shortcut in where you exit out right here, even on average, in the average case, where x may be appearing on uniformly, there's a possibility of it appearing in any one of these spots, it still is linear time. I will not prove that here. So that's linear search. Isn't that fascinating?